We spent a lot of time talking a bit about source. Well, we talked a little bit about microscopy, we talked a little bit about sources, a little bit about lenses. Now there's other things I want to talk about in terms of the instrument, and we're going to carry on with that. Okay. Next thing I want to talk about is we had a lens, we have a beam. We had that beam come down, go through some lenses, and come down somewhere else. All right, but that beam is never perfect. Okay, and you all know, for those of you that do photography, you know you have apertures in your cameras. Well, we have apertures in the microscope too. We're going to talk a little bit about the role of the apertures because it's important to understand how the apertures affect things. So, first of all, and by the way, I tried to use for those of you listening remotely, I tried to use the laser pointer function on my laptop, but then it stops the advance, so I'm not going to bother. So we talked about how lenses take the beam and bring it down. What we haven't talked about is the fact that in addition to lenses, we also have apertures in the column. And the apertures provide several functions. First of all, they get rid of very high angle scattered electrons. Even though we have a lens, we don't focus everything down. So some of these electrons come off at wide angles. We really don't want that coming down the column. So the role of apertures is to restrict the beam. It also, because the apertures cut off some of the beam, control the beam current. Okay? There's another thing that the lenses do is, in addition to controlling the amount of current and the size of it, they control the size of the probe. So we're going to look at both of those in a moment. So first of all, we can put back up. When we put an aperture in, there's several things that happen. First of all, when we put an aperture in, it restricts the size of the probe. So I'm going to show you that next. Let's see. So here's a large aperture, 70 microns, relatively large. And here's a small aperture, 30 microns. What's happened? The size of the probe has gotten smaller. Also, very importantly, is this happens to be a field emission gun instrument. And if you look very closely at the image of the probe, there's no sample in the way here. This is just the beam going through vacuum. We see fringes, okay? Okay. Those fringes are Fresnel fringes. We'll talk about Fresnel fringes a little bit later. But it's very important to realize that as the probe gets smaller, and as the area from which you take the electrons from the source to a smaller and smaller area, the probe gets more coherent. Okay? So in addition to being Fresnel fringes, these are also a measure of how coherent the beam is. The more coherent the beam is, the higher resolution image you will get in your TEM image. Okay? So we can go from a large probe with a lot of current to a smaller probe. We can also go from a less coherent probe to a more coherent probe. Okay? We can also use the lenses. I'm going to back up again. We can also use the lenses to make a small probe and a large probe. This is something called a strong cross lens and a weak lens. Okay? That's in the microscope terminology, that's usually called the spot size of the microscope. Okay? So here I compared the same spot size 3. It's a setting on your microscope. What does it mean? It's the third setting. There's nothing magic about the 3. You have 1 through n. On my microscope, my spot sizes go from 1 through 17. Different instrument manufacturers have different nomenclatures, but this is spot size 3, which is, to me, the smaller the number, the bigger the probe. Why they use that notation, I don't know. It's backwards, but that's what they did. Okay? So now I'm going to go the same size aperture, 30 micron aperture. I'm going to go from a large beam, spot size 3, to a much smaller beam, spot size 9. I'll keep the probe size the same thing. But you notice the number of coherent fringes has increased. Okay? So the beam is more coherent here. But look at that beam really close. There's a lot of noise in here. There's less noise in here. Why? Because there's less current in the probe here. Okay? So it's a more coherent probe. How do I know that? There's more fringes. You can see those fringes go right the way to the middle now. And here they sort of peter out or die out. Okay? No. So a more coherent probe, better resolution in many cases, but less current. Okay. The other thing that the probe does is the condenser lens does, it controls the size of the probe. And the way you do that is by controlling the strength of the lens. Okay. Now, there's one thing to remember about focusing your probe down, and that has to be, are we on an over-focus condition, an in-focus condition, or an under-focus condition? So let's take focus first. When I say the probe is focused on the sample, that means the beams converge. Forgetting about aberrations, they focus right on the sample. If the probe is over-focused, okay, the lens is really strong because it's focusing shorter. So that's an over-focus condition. So the current is greater than what you need to reach focus. And if we're under-focused, the lens is weaker. Okay? Now, that also has an effect on something called the convergence angle. Okay? So in this case, we have a smaller angle when we're in the under-focus condition than in this case. We have a larger angle. That's also important when we talk about imaging, when we talk about under-focus and over-focus. Okay? Generally, we tend to run either at focus or under focus. Can you work over focus? Yes. But notice the beam convergence angle, and that'll be important later, is bigger than in the under focus. So this is a focus probe, this is a under focus probe, and think about it. If I want a parallel beam, what do I have to do? I weaken the lens. So I go to an under focus condition, so probe size decreases. What's going to happen when I weaken the lens? This beam is going to spread out further and it's going to go to a more parallel condition. So the other thing in most microscopes, and this is just a rule of thumb, there's always a knob that you turn to change the lenses. Nowadays, in the past, that used to be a real knob that turned a resistor and that made something happen. The convention has always been when you turn the knob clockwise, you're increasing the current. When you turn it counterclockwise, you're decreasing the current. Okay, that's usually the convention. Okay, particularly on the older microscopes. The newer microscopes, because there's so many lenses, it's hard to keep track. But generally, when you say I want to go to unfocus, you generally go counterclockwise. That's weakening a lens. And generally, when you go clockwise, you're strengthening a lens. Okay, just keep that in the back of your mind. Now, there are a lot of different kinds of microscopes. We're going to be talking later. I think we talk about TEM imaging tomorrow. Yeah. We're going to be talking about TEM and STEM. There's really no difference between the two. Okay? In TEM, we have a beam hitting the sample. In STEM, we have a beam hitting the sample. Okay? The real difference between the two is that in STEM, we almost always have a focused probe. In TEM, you can have the same focus probe in TEM as you can in STEM, but in TEM, we tend to have a more parallel beam. Okay? In STEM, we tend to have a more focused beam. The other thing, the reason it's called scanning, STEM, is because just like in a scanning electron microscope, where we can move the beam back and forth across the sample, you do that in STEM. So that's why it's called scanning. Okay? And that has a lot of advantages for doing some work. Okay, so in STEM, the important difference is we scan the beam back and forth. And remember I told you about deflection coils, that we had deflection coils. And the way the beam scans across the sample is very important. Remember I told you we have double deflection systems, which do two things. They can either tilt the beam or they can deflect the beam. And all STEM systems today have double deflection coils. And what that does is we can take a focused probe and move it parallel across the surface of the sample. Okay? In addition, in addition to having a convergent beam on sample, we have detectors underneath, and we'll talk about that a little bit later. But in STEM, we have multiple detectors underneath. Mainly in transmission microscopy, we have one detector underneath. Usually, it used to be a piece of film. Nowadays, it's either a video camera or a CCD or some sort of electron detector. In STEM, we have multiple detectors down, and we'll talk about how the different signals come about and the information in the different signals that we can get from STEM that we can get in TEM, but it's more difficult. And why do I bring that up? Because the nice thing in STEM is that we can focus the probe down and stop it on, and not only get very high resolution images because we have a very small probe, we can stop probes in different spots and measure spectra, and we'll talk about this in terms of spectroscopy later. Okay. So far we talked about getting the probe onto the sample, hitting the sample, and then scattering. Okay. There are more lenses. We talked about mainly up to this point we talked about just bringing the probe down to the sample. There are also lenses after the sample. Okay. And in those lenses allow us to go between different operating modes of the microscope. Remember, I told you it's a microscope. Well, I called it an electro-optical beam line. Most people call it a microscope, and most people think of microscopes as just doing an imaging device. The important thing that we're going to talk about, is it this afternoon? This afternoon is diffraction work. So we want to be able to change the operating mode of our microscope between looking at an image and looking at something called a diffraction pattern. We'll talk about what diffraction is this afternoon, the basics of it. But the way we go between different modes is our objective lens, our main imaging lens, always stays the same. It either forms an image, so our sample comes here. There's a lens after it that transmits the beam that hits the sample and takes the image from the sample and transfers it to a certain plane. That's the focal length of the lens. Okay? We can look at either the image plane, or we can go backwards and look at a plane that's right here where all the crossovers are. And this plane is the diffraction pattern. Okay? And the way we get either an image or a diffraction pattern is using the lenses after the microscope, and we adjust the lenses to either look at the image plane, or we change the strength of the lens to look at the back focal plane, this plane. Okay? And in one case we get an image, in another case we get a diffraction pattern. Okay, let's see now. So, we looked at an image similar to this before. In fact, it's the same area. And the question is, how do I know when my image is in focus? How do you know it's in focus? You know it's in focus when every electron scattered from the sample goes down to the screen. Okay? Now, how do I know every electron has gone down to the screen? What I look for in an image is the absence of a Fresnel fringe or minimum contrast. What's minimum contrast? Minimum contrast, think about it. If a beam's coming down through the sample and it scatters, and we take all the electrons that have scattered from the sample and bring it down to whatever our detector is, we've collected every electron. We've focused the image. Okay? Now, when an image is out of focus, we get more contrast. Why do we get more contrast? Because we've thrown away some signal. Okay? The Fresnel fringes that we saw, you see when your image is out of focus. Okay? We get either a black fringe or a white fringe, depending whether you're under focus or over focus. When you're at perfect focus, all the Fresnel fringes almost completely disappear, or the contrast is minimized. So the easiest way to focus your image, go to minimum contrast. Now you're in focus. Okay? Now, I mentioned the Fresnel fringes. Where do Fresnel fringes come from? Fresnel fringes are literally a diffraction effect. They come whenever you have a beam hitting the edge of something. Okay? Now, when we looked at the apertures, I showed you apertures and we looked at the beam, there was always a Fresnel fringe there. Okay? That Fresnel fringe came from the edge of the aperture that you're using to form the probe. When we looked at a sample, there's an edge on the sample. We're getting a diffraction effect from the edge of the sample. So we can get Fresnel fringes from a lot of different things. We can get them from the apertures, which forms here, or we can get them from the sample. I think that's the next slide. Yes. Yes. So there's the Fresnel fringe because we have an edge on the sample. Now, here I've adjusted the astigmatism so that my fringe contrast is uniform, right? It's the same width all the way around, okay? Whether it's a black fringe or a white fringe, okay? And I use a simple mnemonic to remember things. Black is over focus, white is under focus. And to me, it's alphabetical. B and O are closer together than W and U. So white is under, black is over. So that's my simple way of remembering, because I always mess it up, to be honest. Okay? And perfect focus, again, is when there is no fringe, we're at focus. So that was the previous, was that the previous image? Let me back up. That one is perfect focus. Okay. Always important to understand when you're taking your image, are you over focus or under focus? Now, I will tell you ahead of time, oops, wrong way. Everybody, almost everybody, likes the over focus image. And they like it because it's easy to see. That's the wrong focus plane to use. You should always be either at focus or under focus, okay? Okay. This is easier to see. Your eye likes it. Your eye likes contrast. Your mind likes contrast. But that's a bad mode to generally run in. You generally want to be either under focus or at focus, and most times it's slightly under focus is always better, okay? Now, I'm going to ask a question. Here are two high-resolution images, and the question is, which one of those is in focus? So you're going to run into this, particularly if you start using the atomic resolution microscope that you have here in Madras. Okay? You're going to get high-resolution images, and you're going to want to know, I got this beautiful high-resolution image. Am I in focus? How do you tell? Okay? Here are two images, and I look at both of these, and I say, oh, I like this one. Why do you like this one? Because there's contrast in that one. That's an out-of-focus image. That's when the contrast is minimized. That's the in-focus image. There's another way of doing this, and when we, on the microscope system here, you have a digital camera. Which camera do you have? Which one? OneView, K2, K3, any high resolution image?
I think it's
K3, okay. Well, in the new digital imaging systems, you have a digital image now, no longer film. I used to do it this way, because that's the only way to do it. In the new cameras, we have a digital image. Because it's a digital image, I can take a Fourier transform of the image and get a Fourier transform of that structure. Here's a Fourier transform of that structure. When I'm out of focus at high resolution, what I will see are concentric rings. Remember, these concentric rings we used before to adjust astigmatism. Well, they also tell you you're out of focus. As we go closer to focus, these rings start to expand. Okay, so we're going from out of focus, closer to focus, more closer to focus, and now you can almost not see the ring at all. Okay? Okay, and if you continue, the rings will start collapsing again. So you'll actually see the rings appear and decrease. So you go through it. And at focus, which is that image, I should have reversed the two. And when you're at focus, you don't see the rings, and it'll be a washed out Fourier transform. Okay, so we said let's focus the image. And the question is, what limits our ability to get a perfect focus? Well, we already said that a little bit ago. It's because we can't build a perfect lens. Let's see, can we go forward? Yes. We can never build a perfect lens. Even with the aberration, with the stigmators to correct astigmatism, we can never get it perfect. And the reason for that is no lens is perfect, even with the stigmators. There are two aberrations that always exist in a round lens. What's a round lens? The kind of lens that we've been talking about. It's spherical. Okay. There are two lenses. One is called spherical aberration. The other is called chromatic aberration. Okay. And the reason that we have these aberrations is I told you about the focusing action of the lens, and I told you that at the entrance of the pole piece, the magnetic field is changing, and that's where all the focusing happens. Well, at that point, the magnetic field is not uniform. It's actually, as you go away from the center of the lens, the magnetic field actually gets a little bit stronger. And what happens when the magnetic field gets a little bit stronger? The electrons bend a little bit more. Okay? When they're coming straight through, they get focused to a certain point. When they go a little bit further out, they get focused a little more. So what happens is we get a range of focuses. That's called the spherical aberration of the lens, and that's proportional to what? The strength of the lens, and also to the angle at which those electrons are scattered through. So it's proportional to some constant, the spherical aberration coefficient of the lens, times the angle at which we're measuring. How can we reduce that? Well, if we put in a smaller aperture, what's it going to do? It's going to reduce that angle, and so it'll reduce the aberration, so the focus point will get better. Okay? That's one aberration, spherical aberration. The other aberration is called chromatic aberration. Now let's pretend, forget about this for a moment. Let's say we had a uniform beam coming in. Electrons of one energy will get focused to one point. Electrons of a different energy, i.e. different velocity, will get focused to a different point. Oh, but you have a 100 keV electron beam and you just told us how nicely focused it is. Well, that electron beam has a source and it has an energy spread. That energy spread can be relatively small. It's only about, depending on the source, for a thermionic gun, it can be about 3 electron volts. For a field emission gun, it can be a quarter of an electron volt. But it's still an energy spread. And that energy spread causes the beam to go in and out of focus of a plane. So we have two aberrations, spherical aberrations and chromatic aberrations. How do we cure this one? Well, we have to change the focus of this. How do we cure this one? We have to make the beam monochromatic. Both of those are difficult. Okay? Mechanically, trying to make a single perfect lens is a fool's journey. Don't try it. Not going to happen. Been tried for years and that never happened. And it's a fundamental limitation of all lenses that you have this aberration. Okay, so there are other ways of getting around it. And we'll get to that in a minute. Okay, so overall, when we look at aberrations of a lens, aberrations are related to the convergence angle that we just talked about, right? The angles of the beam. Notice the angle either coming in or it's related to the angle back here. So we got two angles. Okay, so we can write the probe size, probe diameter, as a function of convergence angle. It's going to, as the convergence angle gets larger, the probe size changes. When it gets too large, it starts getting worse. Okay, so we have a diffraction limit and we have an aberration limit. Okay, this is your spherical aberration. This is your basic diffraction limit. So we have multiple things. The probe size is the image, the diameter of the probes added in quadrature. So you've got the spherical, the Gaussian, and the diffraction limit. I haven't shown you the chromatic aberration effect on this one yet. Okay, so there's an optimum range, and there's an optimum for each angle. There's an optimum resolution that you can get. I'm going to show you the effect of aberrations of those angles. Okay, so first we're going to look at, can we see the aberration? So I'm going to go back here. Can we see these aberrations affecting the probe? Okay, so remember I told you the larger the probe, the larger the angle, the bigger the aberrations. So this is a very large aperture, 150 microns. That means it's a very large angle. We have a focused probe, but look very closely here. Those of you that are looking on the screen can see this. You can see a tail that's coming out. That's the aberrations of the probe. Okay? So it's a very bright focus point, but there are aberrations. There's tail of electrons. If I go from 150 micron to a 70, what am I doing? I'm cutting that out. Boom. I'm going to make that smaller. The aberrations got smaller. Go to a 30 micron, it gets even smaller yet. Okay, so you can physically see aberrations if you look hard enough. The other thing to look at is making sure you have a good aperture. This is a nice clean aperture. It's relatively good. This is a dirty aperture. Okay, bits of junk coming on. Okay, pieces of dirt that's fallen on the aperture. Here's a really bad one. Okay, so how can you tell if your aperture is dirty? Just look at the probe. Okay, if you see things like this, you know you have a dirty aperture. Question, is that important? Well, if I'm only interested in this area, is that affecting me? No. But if I'm trying to focus that beam down really small, these guys are going to get in the way. And now let's just skip that. We can just measure it. Okay, that was aberrations in the probe forming system. We have similar aberrations in the image forming system. The same thing. Remember, we've got the angles coming in and the scattered electrons going through lenses. We have post-specimen aberrations. Okay, it's the same. Sorry, hang on, back up. I'm going to see what slide I'm looking at. Pardon me for a second. I need to stand back. Okay, let me go here. So, what limits TEM image resolution? First thing I was talking about is the probe. Now we've got an image, and I want to get a high resolution image. What's limiting the resolution here? What's the fact that we have a sample, we have electrons scattered through the sample, they're scattered through certain angles. Those scattered electrons now go through another lens system. This is supposed to be a series of lenses, okay? And just like in the probe forming system, where we have an angle-related aberration, we have an angle-related aberration not from the probe, but now from the electrons that are scattered through the sample. How do we minimize that? What do we have to do? We have to minimize the spherical aberration or the chromatic aberration, okay? So we got to minimize that. What kind of resolution can we expect? Now, here's where you have to understand your microscope. You have to understand what kind of microscope you have, what kind of lenses you have. Do you have a conventional microscope with conventional lenses, conventional round lenses, or do you have what's called an aberration-corrected microscope? And we'll talk about both in a minute. So let's first talk about a non-aberration-corrected microscope, a standard microscope. Okay? We can go through and derive a bunch of equations, and I'm not going to do that for you. But I can tell you that we can derive an equation that says the best aberration that you're going to get, the best resolution that you're going to get, delta, is going to be 0.6 times CS, the spherical aberration coefficient of the microscope, times the wavelength of the electron to a power. Okay? Now, what does that tell you? Let's first look at, remember, lambda is the wavelength of the electrons. Higher energy electrons have lower wavelengths. If the wavelength is lower, the resolution is smaller. So you can take a standard microscope, and if you want to get better resolution, what do you want to do? You want to make the wavelength smaller. Why? Because this is to a 1/4 power, that's to a 3/4 power. So in the past, what used to be done, to get a higher resolution image, you would simply go to a higher voltage microscope to give you a smaller wavelength. Okay? So you would start with, original microscopes tended to run around 100 kilovolts, and then they started to go to 200 kilovolts, then 300 kilovolts, then 1,000,000 volts, and there's actually a 3,000,000 volt microscope. Okay, it's the 3,000,000 volt is still in Japan right now. Okay, there are very few 1,000,000 volt microscopes anymore. Most of those have been retired, I guess is right, or decommissioned, right. There's still 1,000,000 volt microscopes in Japan. In the US, I think there's still one left. There used to be 4 or 5 in the US. There's now one left that I know of. It's out in Colorado, I believe. The one at Argonne was decommissioned about 15 years ago. The few other ones were mainly Berkeley's 1,000,000 volt microscopes were decommissioned about 10 years ago. Everybody's gone to a different type of solution for doing higher resolution studies. There are other reasons for going to high voltage microscopes, but that's a different story. Okay, so what does this graph tell us? This gives you a sense of what kind of resolution you can get for different accelerating voltages. So what have I done for you? I've done a calculation for different values of CS, what kind of resolution you can get at different voltages, okay? So if you wanted 1 angstrom resolution, okay? If you wanted 1 angstrom resolution, what kind of CS do you need to get 1 angstrom resolution at different voltages? So at 1,000,000 volts, you only needed a CS of about 1 millimeter, okay? But if you're running down at 200 kilovolts, let's say even 100 kilovolts, to get 1 angstrom resolution, you need a CS in millimeters of 0.001, okay? What's a realistic CS value? Typical CS values nowadays are in the order of, for a conventional microscope, are somewhere around a few millimeters. So is this practical for doing anything? No. We won't build a single lens electron microscope with these sort of CSs anymore. It's not practical. Okay? What you'd have to do is either change the wavelength or somehow decrease CS. Okay? Now, a single lens microscope, you're not going to do that. The new generation of aberration-corrected microscopes do that for you. And we'll get to that in a minute. And what's happened there? What's happened is, over the years, we've slowly gotten either better in CS or higher voltages. So when we compare resolution over the years as a function of year, optical microscopes reached a limit, roughly in the 1920s. They haven't gotten much better. Electron microscopes, remember I told you, started roughly in the 30s, and they slowly got better and better and better, and then they finally reached a limit. That limit was how good we can build a single lens. Around the year 2000, okay, we started getting a new generation of lenses. That is aberration-corrected microscopes, where what we've done is we've realized what the limitation here is, and the limitation is the lens design. With a single round lens, you cannot eliminate CS. It's impossible. You can prove that mathematically, and it's been done years ago. What you have to do is we have to get rid of spherical aberration. We have to get rid of spherical aberration is by redesigning the lens system. And let's see, what's the next slide? Yes. Hang on. Let's see where we are now. Yeah. I'm going to skip this for a moment. I want to skip forward a few slides. Here we go. Sorry, I had things out of place for a minute. So, how do we get rid of spherical aberration? Spherical aberration comes from the fact that we have a round lens. Okay, because we can never get, in a round lens, you can never have a lens that defocuses. You always have a condensing lens. Okay. What we've discovered, or what was discovered by mainly here, there are several people that did it. Albert Crew thought about it years ago. Harold Rosa really developed all the technology for it, and he discovered how to make a non-spherical lens, which is a negative CS lens. Okay, if you take a positive CS lens and a negative CS lens, you can now make CS near zero. Okay, and what that is, it's a series of round lenses surrounded by hexapole lenses. Okay. This is a very complex lens system now. It's no longer a single lens to focusing, but it's a group of lenses. Okay, I'll show you some images later of what a image correcting microscope looks like. It no longer has a single objective lens. It has, depending on which microscope you're looking at, somewhere near 100 lenses in it. Okay, and 100 lenses, it gets very complicated to align and do it. One of the reasons that it took so many years to get aberration-corrected microscopes is that we couldn't physically, manually do all the corrections. Once we got the computer control and the computer processing power and the digital detectors, we're able to do all these corrections semi-automatically. They're never perfect. You still have to do some of it yourself, but it's speeded up the process enormously. Okay. So what's happened again is we've gone from single lenses to multiple lenses, and those multiple lenses consist of a round lens, quadrupole, hexapoles, octopoles, dodecapoles, and what they do is they take a lens that had aberration coefficients and they bring all of the lenses back to have a single focal point. And now CS goes to near zero. In fact, we can even make CS even slightly negative. What does that mean? It means we can take an image that looks like this and actually get down to half an angstrom resolution. Remember, I told you a few minutes ago, let's go back. Back to here. Conventional resolution, if we go back in the 90s, was in this range. You know, 1 to 3 angstroms was just about doable. But in order to get 1 angstrom, you really needed a really small CS, and that wasn't practical. Okay? It's only when we started to get CS very small, by using very small angles, that we started to get resolution limits in the angstrom or sub-angstrom regime. Okay, let's go forward now. Question? Yes.
CS unit is
I'm sorry, wait a minute. I got to get a little closer because I don't hear well.
CS unit is mm or micrometer you have given. What that actually mean? Where is that mm comes from?
Millimeters?
In the microscope, I must.
Yeah, it's so the question was, where does the CS come from? How is it measured? I always gave it in millimeters. Okay, it's a function of the focal length of the lens and the gap in the lens. Okay, the pole piece gap, the space between lenses. Typically, the focal length and the CS are about the same, and the typical focal lengths in objective lens are related to about a third of the gap. The typical gaps, space between the pole pieces, is, depending on whose microscope you get, could be anywhere from 1 millimeter to 8 millimeters, okay? More typically, I think the gap you have, I think you've got a Titan Super Twin, right? So you've got about a 5 millimeter gap, okay? The way high resolution used to be done was two ways. It was either increase the accelerating voltage because CS was constant, or decrease the size of the gap, make the gap smaller, which changes the focal length, which changes CS. So if we make the gap smaller and smaller and smaller, CS gets smaller and smaller. Okay, at a certain point, if the gap goes to 0, CS will go to 0, but then you can't get your sample in. So there always has to be a gap. So the high resolution microscopes that we used to have in the past used to have very small gaps, so very small spaces, and you would just barely get the sample in. But when you get in those configurations, you can get a sample in, but you can't do anything to it. You can move it a little bit. Can you go up and down a little bit? Not much. Can you tilt it? Almost none. Okay. Nowadays, the kind of material science experiments we do tilting experiments. So you want to be able to tilt the sample. What's a good number? You'd like to tilt at least 45 degrees, ideally maybe 60 degrees. Okay. If you're tilting something 60 degrees, think about it. If your sample is 3 millimeters in diameter and you're tilting by 60 degrees, you need a gap that's what? Cosine of 60, so you need a gap of near 5 millimeters. Okay, so 5 millimeter gaps, like we have at the machine here, is about standard. 5 millimeter gap, your CS is going to be a couple of millimeters. Okay, so you're not going to get better than that because of the gap. Okay, did that answer the question?
Yes, but CS value is not just the gap. It is actually that.
It's a parameter.
That millimeter is the gap plus something you told, the focal length of.
CS is CS is a numerical parameter that we use to calculate the parameters of a lens. It happens to be a constant, okay? And that constant is related to the design of the lens. Lenses with large gaps have large CSs. Lenses with small gaps have small CSs, okay? Let's put it that way. The other way to relate CS is the CS is, not only is the gap related to CS, but the gap also is related to the focal length of the lens, okay? So my way of thinking is the focal length is related to the gap. The bigger the gap, the bigger the CS, the longer the focal length. The bigger the focal length, the worse the resolution of the microscope is. Does that help? Good. Good question. Thank you. All right. Let's see, where are we? We're talking about, corrector, excuse me, I need a drink of water for a moment. And I just need to go back to see where I was. That's forward. Yes, so we talked about correctors. Good question about CS, where it came from. The CS comes from the lens design. The bigger the gap, which means more space, which is what we want to do for doing experiments, the worse the resolution. What do we have to do? We have to get rid of CS. How did we get rid of CS? With a conventional lens, you can't. You only have to either change the accelerating voltage or make the gap smaller. We want the gap bigger. So what we've gone through is develop new lenses to give us a round lenses always have a positive CS. Other lenses have a negative CS. By adding other lenses to the round lens, we can now get a net CS which is near zero. And nowadays, because of the number of lenses we add, we can actually make CS negative overall. Okay. And what does that mean? It improves the resolution of our microscope. We now have microscopes that can routinely do 1 angstrom resolution with a 5 millimeter gap. The machine you have downstairs should easily, it's a 300 kV? 300 kV super twin with an image corrector, right? You should easily be able to get to the 1 angstrom regime with that machine, okay? What does that mean? That means we can get images where we can actually image single atoms, okay? And I'll show you other images in STEM later that show you even better resolution. All right, so we can make these correctors. Now I talked about aberrations of lenses. That holds for all lenses. All lenses have aberrations, whether it's in the probe forming system or the imaging system. Modern microscopes today, you can buy a corrector. Costs a lot of money. A corrector costs about $1 million, in addition to the cost of the microscope, okay? So you can put a corrector on the probe forming system, on the imaging system, or on both. So now if you put it on both, that's the cost of the microscope, $1 million plus and $1 million here, that's another $2 million on top of everything. So here we have just an image corrector, right? Okay. The instrument I have back at Argonne has a probe corrector only. I don't have an image corrector. It all depends on the kind of work you want. There are a lot of microscopes that have double correctors. Okay. It's very expensive and very tall. An example of, I think I'm going to just show you some pictures of correctors now. So this is the electron microscope at the University of Manchester. So what we have is a field emission gun, we've got condenser lenses, and then we have something that's as big as all the condenser lenses as the probe corrector, sample, and then no image corrector, okay? Let's go. Okay. Why do we want to do, what limits our resolution in a microscope? One of the things that limits the resolution of a microscope is, I'm going to go backwards now. I want to go back to this slide. Okay. If we want to do a high resolution image, we want to transfer the information from the sample onto our detector. And that information has to go through a series of lenses, okay? And I already talked about aberration correctors to minimize the aberrations. That'd be great, okay? So we talked about that. I'm going to go forward now. The thing we have to worry about is that we have information that's generated at the bottom of the sample, and it's got to get transferred through a whole series of lenses to a detector. In that transferring process, we're going through a number of lenses, and each one of those lenses contributes to the contrast. Okay? What does the aberration corrector do? The aberration corrector minimizes the oscillations in the image that happen due to the various focal points of the lenses. Okay? So what happens when you have a microscope that is non-corrected, so just a standard microscope, okay? The information, the phase contrast transfer function, the information that's transferred depends on the resolution you're trying to get, and at a certain point, information is no longer transferred. So that's called the resolution limit of the microscope. And that can be determined basically by CS. Remember the formula I told you? 0.6 times CS to the quarter, lambda to the 3/4. That defines that angstrom limit, okay? Resolution limit. Now, if we want to go to better resolution, what do we have to do? We have to change CS. Okay? We can do that by putting an aberration corrector in, which reduces CS. If it reduces CS, it extends the contrast transfer function to a new resolution limit. Okay? This is a conventional microscope. This is an image-corrected transmission electron microscope. Notice that we've moved this down in frequency space. This is angstrom resolution now. If we wanted to get half an angstrom, we can move it further down. Okay? If I wanted to move it even further, I have to correct not only the spherical aberration, but also the chromatic aberration. Okay? If I wanted to move further, we have to decrease the energy spread of the source. So we can do that two ways. we put in a different source, a field emission gun source, or we put in a field emission source with a monochromator to reduce the energy spread even further. And that's how we move this even further. Today, we can also build a corrector to correct for chromatic aberration. That's a very complicated device.
Can I ask a question?
Sure.
Suppose if you just put a monochromator,
Yeah.
even without correcting the probe, will it be of some use?
So the question was, if we put a monochromator on a machine, even without a spherical aberration corrector, will it be of any use? And for high-resolution imaging, will it improve it a little bit? Yes. The corrector would be, spherical aberration corrector would be better. Okay? Now, a monochromator on top of in your probe forming system will give you other opportunities. So there's other things you can do with a monochromator that would be beneficial. If I was going to give my druthers, if somebody said, what should I put on? Should I put a monochromator or an aberration corrector? I would say put in an aberration corrector. Where would I put the corrector? Would I do an image corrector or would I do a probe corrector? That depends on the kind of experiment you want to do. Okay, if you're interested in having small probe work and doing analytical work where you're interested in a small probe, the probe corrector is better. If you're interested in doing high-resolution imaging, high-resolution TEM imaging, then the image corrector is better. Okay. Could you put both in? Sure, but that gets really expensive. Now, there are people that, if you have a funding agency that'll do it, go for it. Okay. Okay. I was going to say, in addition to doing the spherical aberration, we can put chromatic aberration correctors in. Those are even more complicated devices than a simple spherical aberration corrector, which only has maybe 50 or 60 lenses. Okay, I'm probably exaggerating there, but it's a lot. In a chromatic aberration corrector, you not only have to have spherical aberration, but now you also have chromatic aberration. And the only way you can do that is, in addition to having electromagnetic lenses, you have electrostatic lenses. Okay, so you have a combination. So it's both voltage, electrostatic lenses and electromagnetic lenses. And now you can correct both. Okay, this is what a CS plus CC corrector looked like. And you notice it's 83 centimeters tall. And this is the one that's got, let's see now, here we go. These are all the lenses. This is just the corrector, which is that bit. And you can count how many lenses. These are just the main lenses. There's additional lenses on top of it. And you notice, if you had to manually adjust all of those lenses by hand, can it be done? The very first ones were done all by hand. Yeah, the very first CC corrected machine was done all by hand. Yeah, rapidly learned that they're not going to do this by hand very often. But so this is one of my colleagues, J.G. Wen, back at Argonne. This is the world's first CC CS corrected microscope. It's still at Argonne. It's about 10 years old now. It's about to be decommissioned. If somebody wants it, they'll sell it to you as a used machine. It's a really complicated beast. But it was a 8300 kV. It had a 5.4 millimeter gap. And it did a really good job. Just to give you a sense of what the resolution change was. This, again, remember, this is the phase contrast transfer function. Where this goes to zero, that usually the resolution is defined by the first times we cross zero, okay? And so the resolution of this type of machine without a corrector was just about 2 angstroms. With the CS plus CC corrector, it got down to below half an angstrom, okay? All right. And what that means is we can get very good resolution even at lower voltages. So at 80 kV, we've gotten down to 1 angstrom level on that. That was the first on that particular machine. This happens to be my machine. It's a 30 to 300 kV probe corrected machine. Okay, so my probe corrector, remember in the other machine I showed you at Argonne, is an image corrector. It's all down here. Here I have conventional lenses. My probe corrector takes up that amount of space. It's a little bit smaller because it's only CS, it's not CC. What I've decided to do is instead I put a monochromator on. So I have a probe corrector plus a monochromator. And that allows me to get probe sizes. And this is a real image from my machine. The spacing of these two atoms, this is a gallium nitride spacing. You can see the space between those two atoms. There's a line between them because they're separated. That spacing is 63 picometers. Okay? Okay, so that means I have a probe size that's probably about 50 picometers. Okay? And with that, I can do not only imaging, which is nice, but I don't do imaging. I do mainly spectroscopy. Okay. Now, we've actually gotten farther than I thought we would get. So let me just see. I've talked about a lot of things. I'm going to give you a few references now. These are going to be in your notes. So if you want to know some, I talked a huge amount of things. I covered a lot of territory. And I'm getting dry, so it's getting to the point where I need to stop talking, and that's good because I'm getting near the end of these slides. Some basic references on electron microscopy. We'll be using a lot of these later in the talks later about defect analysis and diffraction techniques. Okay. Now, I think it's about noon, so we're finishing a little bit early. But to be honest, I need a break. Let's see, what else do I have here? Yeah, why don't we take a break now? When do you want, let's just stop for the morning now, mainly because I need to stop talking. I'm getting hoarse.
We can start at 2, is it okay?
That's fine for me.
2 o'clock is fine?
Does 2 o'clock sound okay? Take a break?
Yeah.
When we come, sorry, I do need a break. When we come back, we're going to start talking about, so we're done talking about the instrument. So what did we talk about today? We talked about the electron sources, okay? We talked about the lenses. We talked about aberrations in the lenses. We talked about the functions of apertures. We talked about beam control, stigmators, how to adjust stigmatism, how to adjust focus, how to recognize when you're in focus, how you recognize when you have an astigmatic image. We now talked about the functionality of the instrument. We didn't talk about things like vacuum systems. That's a whole nother sub-talk. We didn't talk anything about sample prep. That's a whole nother topic. When we come back from lunch, we'll start talking about actually using the microscope. So far, I just showed you examples. We're going to start talking about first electron diffraction in the microscope. So I'll give you some basic feed-throughs on what electron diffraction is and how we get information from electron diffraction. And then Hamish is going to come in and talk about some advanced diffraction technologies for doing microstructural analysis and defect analysis. That will cover all of the afternoon. So we'll talk mainly diffraction this afternoon. I think that's right. Let's look at the schedule. And then tomorrow morning, I think we're doing imaging. Is that it? Hold on. Let me go back and look. Yes. Diffraction this afternoon. Tomorrow morning, we'll talk about imaging. And then we'll talk about spectroscopy tomorrow afternoon. Okay, so diffraction this afternoon. I'll start out on basic select area diffraction, basic diffraction information, and then Hamish will talk about the advanced diffraction. And then tomorrow we'll talk about imaging and contrast, defect analysis, and then inelastic scattering tomorrow afternoon.